Hello, everyone. Although the title says on the ways that planetesimals were analogs to terrestrial planets, it won't perhaps surprise you to hear that my main point is that they were not analogs to terrestrial planets, but in fact very, very different from them. And so I'm going to talk about differentiation and deep silicate processes, what sort of surfaces or crusts there might be, and also a little bit about cores, and kind of give an overview of where we are. Now, in the middle here, you see cartoons of different sorts of planetesimals. And now, of course, we think that something like 1,000 or more planetesimals formed from the gas and dust in the early disk, bodies tens to hundreds of kilometers in radius. And on the left of that arc there, you see bodies that are undifferentiated. This is the classical onion skin model where the interiors of these bodies metamorphosed and metasomatized from heat and fluid but did not melt. And at the top, bodies that perhaps melted partially differentiated into a core and what might be called a mantle, but they retained a primitive crust. And then on the far right, bodies that perhaps melted entirely. It could be that Vesta falls in that category. And of course, most of what we know comes in the form of the shrapnel on the right, which are the meteorites that we find now falling to Earth, and with increasing information from the asteroid belt. And so a question might be, what are the fates and the compositions we'd expect to find in that meteorite collection based on these melting and differentiation models? And in what ways are they similar to or different from the Earth? Well, one of the first things that's going to happen is that volatiles will be released through heating of the silicate phase. And what you see here is a graph that shows pressure on the vertical axis and temperature on the horizontal axis. And that dashed line through the middle is approximately the pressure at the center of a Vesta-sized undifferentiated planetesimal. And so this is work that Roger Fu and I did that just came out earlier this year, where our point is that as the temperature rises inside this body from the effects of radiogenic heating of the short-lived radioisotopes aluminum-26 and iron-60, that metamorphism can be done as you create different kinds of hydrated silicates, but eventually the temperature pressure curve of your small body is going to cross an area where there is no hydrous phase, no solid hydrous phase, but instead a free fluid phase before silicate melting begins. And extensive work has been done on this by Ed Young and his group, and they found that in bodies 40 kilometers radius or less, these hydrous fluids would circulate within the body, continuing to metamorphose it and metasomatize it. But in bodies greater than 60 kilometers in radius, that fluid would percolate toward the surface so fast that they would not even metamorphose the minerals and create hydrous minerals, but instead dry the interior and then create either a volatile-rich layer or be lost into space. And so the main point that Roger and I were trying to look at is what happens then to the subsequent silicate melting. So you see on the bottom a bar that shows progressive radiogenic heating, starting with an early accreting planetesimal on the left and this efficient loss via Darcy flow of fluids in the middle. And what we found was that whether any remaining primitive crust could be retained or whether the surface would be covered with basalt and become an achondritic crust depended upon the bulk composition and the degree of melting. And so on the top right, you see positively buoyant melts where an achondritic basaltic crust, a true crust, would be formed. This is by secondary melting. Ordinary and enstatite chondrite bodies, bulk compositions indicate that that silicate melt would be buoyant and erupt. But we found, and you see on the bottom right, that the CV and CM carbonaceous chondrite bodies have melts that in many cases are dense and they would be negatively buoyant, and any chondritic crust, I hate to call it a crust, it's not truly a crust, but it's hard to remember to say lid every time or some other word. The primitive material that was left on the surface or accreted by later impacts would be preserved. And so this is certainly a very different melting process that happens on our terrestrial planets today. There's really nowhere that we know of where radiogenic heating and primary dehydration by such is the main way that silicate melts are made. And yet that's the case on these early forming planetesimals. So that way they are definitely not an analog to the Earth or other terrestrial planets. Now, Wilson and Kyle have done some quite extensive work on what would happen if you had volatile-driven eruptions. That is to say, you had a positively buoyant melt that melted from a silicate that had not been efficiently dried through radiogenic heating. And what you're seeing here is the size of the pyroclast diameter on the vertical axis, the asteroid radius, or the planetesimal radius on the horizontal axis, and each of those curves shows the parts per million in volatile content of the magma. And so if you looked at the dashed line that goes vertically up through the middle, that's for a 50-kilometer radius asteroid. And if you see where it crosses the 2,000 parts per million curve right here, this implies that all pyroclasts smaller than about 11 millimeters would in fact achieve something greater than escape velocity and be lost, and only the larger ones would fall back. And so that gives you an additional difference, a significant difference from our terrestrial planets, where an explosive volcanic event could actually preferentially cause small and volatile rich material to be entirely lost from the body forever. Now, let's talk a little bit about what might be happening inside of these bodies with any partial or complete melt that forms inside. Because one of the great mysteries for all of these models is why we don't have a lot of meteorites made of olivine, and where we didn't find lots and lots of olivine on Vesta. So if you're fractionating an internal magma ocean, why does it not end up creating a huge amount of olivine? And what these little ternary diagrams show, if you look at this inset one, what I'm doing is plotting compositions that could be bulk compositions of these bodies on a ternary diagram, and looking at whether the first crystallizing material would be olivine or the first crystallizing material orthopyroxene. And if you see here is our area of bulk compositions, and only the lower pressure eutectics and cotectic lines really apply to these small bodies. So all of them fall really in the olivine first field. And so why do we care about which mineral crystallizes first? Because that's what we would find to be the only thing that's likely to be able to settle at the core mantle boundary. It's very consistent with models for the formation of pallasites where they have olivine. But the point I want to make here is that on a body the size of Vesta, you can see on the left, its adiabat for any kind of internal magma ocean lies well between its solidus and liquidus in that green field over its whole pressure range, unlike it does for how in larger planets. And what this means is that there's going to be a high crystal fraction on a body with a very low gravity over the whole crystallizing period. And that means that it's very unlikely for the melts to fractionate efficiently and actually create any sort of monomineralic or richly enriched layer. And in fact, the interiors of these bodies are likely to crystallize in bulk and not create the vast amounts of olivine-rich material that we're really anticipating to find in the meteorites. So that's another difference from the Earth. Now, I talk about cores a little bit here, having talked about what might be called a mantle and what might be called a crust or a lid. There is, I find, extremely interesting and increasing evidence that these planetesimals, many of them had core dynamos. Here, one of the pallasite bodies was shown to have a core dynamo by Tarduno et al. 2012, and the data from Fu et al. In 2012 also showing that Vesta had a core dynamo in its time, and we had some data demonstrating perhaps that the Allende parent body had a core dynamo. And so core dynamos actually are something that is more held in common between terrestrial planets and planetesimals than what happens in the silicate fraction of the body. And I find that to be really extremely interesting, that we find a better analog in the core than we find in the mantle and on the crust. And so here's a figure prepared by Aaron Scheinberg for a paper that's in PrEP, and I want to also point you to the other references at the bottom, people who have been working on this for some time. On the top row here, you see schematics of cores that crystallized from the inside out, and in the bottom row, from the outside in. And when I first learned about this by talking with Joe Goldstein many years ago, I was really flabbergasted because I'd never really heard of a core crystallizing outside in. And the compelling data from the iron meteorite collections that we have is that some of these bodies really did crystallize outside in and some inside out. Now, isn't that a fascinating conundrum? And not only that, but there's the suggestion that they might just not crystallize neatly in this way in clear concentric circles, but there might be snow or dendrites that form and create a more complex body in the end. And here in these figures, a sulfur-rich residual melt, what might be left over after you crystallize most of your iron, nickel, metal, is shown in yellow. And so in the inside-out crystallization, it might be trapped near or on the surface, and in the outside-in, it might be trapped in the interior. And of course, I have a very strong ulterior interest in this because we would like to go look at the asteroid 16 Psyche, which is very likely to have crystallized outside in. And this becomes an even stronger analog to terrestrial bodies when you think about the recent information from the MESSENGER mission on Mercury that that core might have a solid layer at its surface and a solid layer in its deep interior with the liquid in between. And so we're looking at crystallization sequences in these meteorite collections and perhaps in the iron asteroids that we have that do have direct analogs to the terrestrial planets. Let's see, so then I want to just summarize here saying that some of the many ways that planetesimals are not analogs to the terrestrial planets. Radiogenic heating may dehydrate the silicates before they ever melt. You might have a surface that is primitive and in fact either never melted because of radiogenic heat in the interior never being sufficient, or where primitive material was plated onto the surface after the interior processes were finished. Or it's possible that with interior melting these melts might actually migrate to the surface, either covering the surface as lava or as pyroclasts and forming something that might be called a true crust. But in both cases, quite different from terrestrial planets in the material it's melting and the way that it's melting and the things that produce migration quite different. An interior silicate magma ocean is not likely to fractionate because it would have either not have melted to completion, or it would have a very high crystal fraction and not allow crystal settling, except perhaps just the first few % of crystals would be the only ones that could settle. But then finally, the ways that these bodies might be more closer analogs or more useful analogs to terrestrial planets is in their core processes. And this very interesting information that cores might solidify inward or outward, depending largely on the thermal properties of how much silicate is left on the surface. And also that core dynamos may actually have been quite common in these small bodies. And as we find every place we really look thoroughly in the solar system, we find out more about dynamos happening. That seems to be a really ubiquitous characteristic of a metallic core and something that we can learn more about through both the meteorite collection and the asteroids. So thank you very much.
Thank you, Lydie. There's time for several questions. Please use the microphone or speak loud.
Wonderful talk. So if the planetesimals were already dehydrated so much, where does the Earth have its water? What about Venus?
I wonder about, of course, there would be plenty of planetesimals that were not large enough or early enough forming to have melted, and then there would be those that would only melt partially. But it seems to me, based strongly on Ed Young's work, that you might expect a really heterogeneous body where the deepest interior would be dehydrated and the material near the crust would actually be enriched in fluids, and you would be hard-pressed to find a sample that was an average bulk composition on those bodies.
I didn't anticipate that.
How do bodies like Ceres fit into this picture of planetesimals?
So here I've really been talking about bodies that are not extremely enriched in ices.
Okay.
And then you get into a sort of a gradient, don't you, or a continuum with bodies that have less and less rock, which carries the radiogenic material, more and more ice. And a good place to start and then look for references to that, of course, is Julie Castillo's work, because she really had examined the effects of heat of fusion of the water ice when you try to melt it with radiogenic heat, and you can't get as far as you might like. Yeah.
Thank you.
Thanks.
Another question?
Yeah, I'm not sure that, the water in the early, in the planetesimal would exsolve and, leave the body. It might recirculate in a hydrothermal system.
Right, right. And so Ed Young talks about whole body hydrothermal systems, and then it seems also likely that you would have more near surface hydrothermal systems, and perhaps they would then repenetrate to depth and re-metasomatize at depth. And I would think that these are all things that we might be able to test for if we look specifically for those processes in the meteorite collection.
If there's no more question, thanks again, Lindy.